Hey everybody, and welcome to another physics video. For this lesson, we are going to focus on torque and moment of inertia. Before we talk about torque, we should revisit the concept of forces. Force, in its most basic definition, is a push or pull. However, it's completely possible to apply a force to an object and it does not travel in a linear direction. It may actually cause a rotation instead. This brings us to the topic of torque. Torque is a quantity that measures the ability of a force to rotate an object around some axis. Just as force is a push or pull, torque is more like a twist or turn. Torque is represented by the variable tau and is equal to the force times the radius by sine of the angle. Let's use a door as a reference on why these variables matter. It makes sense to apply a force to a door to swing it open. But where does the radius and angle come into play? The radius is in reference to the axis of rotation, and comparing to a door, the axis of rotation is the hinges. We know from experience that opening a door is easier the further away we are from the hinges. What about angle? The angle is between the force applied and the radius towards the axis of rotation. When we attempt to open a door, we naturally apply a perpendicular force to open the door. This would mean an angle of 90 degrees would give us the highest torque. Let's do one quick example. A force of 5.0 newtons is applied near the edge of a 1.5 meter door in length. If the force is applied directly perpendicular to the door, what is the magnitude of the torque? We know the force, the radius, and the angle to be 90 degrees. We can multiply all the values together to get the torque of 7.5 newton meter. Newton meter will be our units of torque. Though this example asks for the magnitude of the torque, torque is considered a vector with a possible direction of clockwise or counterclockwise. Let's try a second example. Oliver, with a mass of 56 kilograms, and Barry, with a mass of 43 kilograms, want to balance on a 1.75 meter long seesaw. Where should they place the pivot point? We're only given three known quantities in this problem: the mass of Oliver, the mass of Barry, and the length of the seesaw. Drawing a diagram, I'll have Oliver sit on the left side and Barry on the right side. The pivot can't be in the center, as the masses of Oliver and Barry are not equal. Barry requires a larger distance from the pivot to compensate for his lower mass. Barry and Oliver here are exerting torque, which combining together produces a net torque. However, the seesaw is not twisting but balancing. Therefore, the net torque should be zero. Also, you notice Barry's torque is negative because his weight will cause the seesaw to rotate clockwise. With that in our equation here, we can say the torque of Barry and Oliver must be equal. The force that causes the seesaw to move is their force of gravity. Therefore, we can define the torque as Oliver's force of gravity times Oliver's radius times sine theta equals to Barry's force of gravity times Barry's radius times sine theta. We can cross out gravity, and the angle is going to be 90 degrees. This leaves us with Oliver's mass times Oliver's radius equals to Barry's mass times Barry's radius. We're stuck as there are two unknowns. We can say that their combined distance from the pivot equals the entire seesaw. Oliver's radius plus Barry's radius equals 1.75 meters. We now have a system of equations and can solve. Let's isolate the radius of Oliver. Using substitution method, we can calculate that Barry needs to be 0.98 meters away from the pivot, and Oliver needs to be 0.79 meters away. Inertia was a concept earlier mentioned with forces. Inertia was about the resistance to a change in motion. Its resistance to change had much to do with an object's mass. The more mass an object had, the more inertia it also had. But when we talk about inertia, we were talking about the resistance to change in linear motion. An object can resist change rotationally as well. This is called moment of inertia, resistance to rotation. Just like inertia, mass is also a factor in the moment of inertia. However, since it is about the resistance to rotation, it also depends on the radius or distance from the axis of rotation. Lastly, moment inertia varies based on shape. Listed below are a few examples, but are not a complete list. Let's try a brief example. A twirling baton is a thin rod with two round objects at the end. The objects are 0.30 kilograms each. The length of the baton is 0.65 meters. The mass of the baton is negligible. First question asks, what is the moment of inertia if it's rotated about the midpoint? And the second question asks, what is the moment of inertia if it's rotated about the endpoint? The baton's mass is being ignored, and only the mass of the object at the endpoints are considered. We're using the moment of inertia for point mass as the shapes of the objects is unclear. To calculate the moment of inertia if the baton is rotated by the center, the mass of the endpoint is multiplied by the radius squared. The objects are 0.325 meters from the center, as it is considered half of the baton. The moment of inertia is calculated to be 0.031 kilogram meter squared. Since there are two objects, we can multiply it by 2 to get 0.062 kilogram meter squared. To calculate the moment of inertia, if the baton is rotated by the endpoint, the radius now is the entire baton length, 0.65 meters. And only one object is rotating as the other object is remaining at the center, or in this case, the axis of rotation. For this, the moment of inertia is 0.126 kilogram meter squared. Alright everybody, that concludes our video on torque and moment of inertia. Hope you found it helpful, and thank you for watching.